My name is Steve Goodman, and I currently work for NOAA in the satellite program. I'm the chief scientist for the new generation geostationary satellite.
9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of NOAA's GOES-R, America's most advanced weather eye in the sky, elevating environmental intelligence to new heights and saving lives.
And I started on this path 38 years ago. When I was still in graduate school, we were looking at, could you put a lightning instrument in geostationary Earth orbit to look down at storms? And we didn't know how to do it. And we took our concept, which was supposed to be originally on the GOES-13 satellite, which is currently in the Atlantic, and the imagery's downstairs in your lobby. But the timing wasn't right for such an instrument, so we kept development going. And what we did is we flew the instrument concept on the low Earth orbit satellite for 15 years. And so we have a near global distribution of lightning activity, including for Argentina, from the research side of things, but not operational. And the imager itself is the first new imager in 22 years. So we've been flying imagers in geostationary orbit since the first weather satellite 40 years ago. This current satellite is staring at the Earth, and we're able to put new instruments on for the first time because we typically purchase the new satellite systems in blocks of 4 satellites, and they last a long time. So it's a very long time before we can refresh the technology. So now that we've been able to refresh it, we have an imager that has 5 times the refresh rate of the imagery, faster image updates, 4 times the spatial resolution, so we see features we never were able to resolve before. And we have 3 times as many spectral bands, or the different colors that we're able to see of the clouds and the Earth and the planet. But now the new instrument lets us take this fast imaging and also continue to provide you with 15-minute or even 5-minute, depending what mode we're in, images that cover all of South America. So one of the things that the geostationary satellites provides for the global forecast models is something called the atmospheric motion vectors. And what that is imagine looking up at the clouds. You see a face in the cloud sometimes, and you see how it moves. And so we can track moisture features and also cloud features, and we take image after image after image. And if we take 3 images, we can see how things have changed. And we can get a motion vector, like having a wind direction and a magnitude. And that information from the geostationary satellite is our main input into the global models, because much of the Earth does not have balloon launches where we're able to map the temperature, humidity, and winds. So this way we're able to provide a wind measurement to the models. Now, why is that useful, aside from the fact that all the models can use that data, is that because of the higher spatial resolution that we have, we're able to see cloud features in much greater detail. So when we're trying to track them, we can see the features better, and because of the higher resolution, both in space and time, we can get the height of the cloud much more accurately. So it doesn't help you if you can have a good wind speed and a good wind direction, but you put it up too high or you put it too low. And so because of the spatial and temporal advancements, we're able to do a much better job. And I've been told that the wind speed bias that we have generally it's too fast. We're able to improve it by about 1 meter per second, which may not sound like a lot, but for the models it's very significant. So we get the velocity of the wind tracers more accurate, we get them at the height, altitude more accurately, and that will have an impact on the global models. And it doesn't just stop there, because your regional model that you run at high resolution, say for the country, starts with the boundaries of that model from the global model. So if we improve the global model, we automatically should improve your regional model. And that's the #1 contribution for numerical weather prediction. And we also hope that the computers aren't as advanced as we need them to be. Believe it or not, we have so much data that we're producing that we would like the computers to be able to take that data, and we can derive these winds not every 15 minutes, say if we're taking a full view of the hemisphere, but we could do it every 5 minutes or every 1 minute. And then if we could do it every 5 minutes, you could see an impact even in your regional model. Directly take that information into the regional model, because that's too quick an update for the global models. But we may be talking, that's 5 years away from right now for us to learn how to use it. So the imager has faster update rate, more spatial resolution, and more spectral bands or different colors of the spectrum that we can see. That means we can see things we couldn't see before. For example, when you have a fire, you see the smoke from the fire. We can now detect that very well because we have a band in the blue. We don't have a band in the blue today, and you see the smoke very cleanly. We see in the water vapor, we have 3 water vapor channels now. We currently have 1. With the new water vapor channels, we can see deeper into the atmosphere, and the forecasters are very excited about that. Most of the moisture is in the lower part of the atmosphere, and we've always been looking high up. And so now with the lower altitude of the water vapor where the action is occurring, the storms are developing, the atmosphere is unstable, we're able to pick out how that's changing quickly in time, and we can see strong gradients of moisture, which leads us to know where the instability is in the atmosphere. So if a storm, say, is just beginning and it moves into an unstable region that's becoming more unstable, your forecaster knows to pay attention because that's likely to become a severe or high impact storm. We can do more and better with the new capabilities that we have. And then the GLM, which is a wholly new instrument, is able to map all the lightning that's occurring in a storm. So there are ground-based networks that just detect the lightning going to ground, and it goes to ground, and it goes to ground. But this satellite can detect lightning channels which are in the cloud. And why is that important? Because it's the total lightning activity that's related to the intensity of the storm, not just that it struck the ground here. And even more amazing is when we're able to look at the whole lightning channel itself, what we've learned, and as a realization for the forecaster, is that I may see lightning strike here and strike here and strike there, say within a half a second. And they think that's 3 separate lightning flashes, but it's not. It turns out there's one long lightning flash, and it put a strike to ground here, 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 and elsewhere. And so the complexity of the lightning was not really understood or seen so well by forecasters, and this will make things more accurate. And one thing the lightning mapper looks like it could do for you is not only point you to the most intense storm cells, say in a line of storms, which one's most intense, or even over the ocean where we don't have radar, the lightning mapper, the imager can help you for all your transoceanic flights. And that'll be very helpful. And the last thing is the lightning mapper not only sees the cores, but it sees lightning that propagates horizontally from the main line of storms. And suppose you're outdoors and you're just playing golf, or you're walking, or you're swimming, or you're boating, or you're at an airport. You're playing, yes, and you're at an airport, playing football, right? You're at an airport and you're unloading luggage, or you're fueling the airplane. The lightning that you see may be 100 kilometers away. What you don't realize is the lightning is propagating overhead. But we can see that, and so we can tell the public and the users that, hey, the lightning risk for you is not 0. There is a risk because the lightning in the distance is coming overhead and could go to ground where you are. So that becomes a public safety hazard. So in the end, between the imager and the lightning mapper and all these new capabilities, we should help save lives, property, and so forth because of the new capabilities. And these will be with us for the next 25 years. So there's been a good question about how do we disseminate the data? How can we best disseminate the data? So there are certain countries which can afford to buy the receiving station to get the satellite data directly. When it comes down to the ground, it's processed, sent back up to the satellite, and then transmitted to the users. So if you have that, what that means is that you can get all the data products and you can get them at full resolution. So you don't have to resample them because you have a limitation of bandwidth. You can get all the data received, and you can get it timely. If you don't have such a satellite reception disk, you have to find another way to get the data, say through the internet, which may not be as reliable and it won't be as quick to get the data. And also, a lot of users want access to the data through the internet, and we have to control that bandwidth because there's so many users, we can't support everybody with the full volume of data, whereas if you have your own satellite dish, then you're not restricted. So the advantage is, since you're able to do it, is you will not be restricted in all the data that you can bring in, and it'll be as most timely as you could want it to be. There's been studies here before. There's a South Atlantic low-level jet, and they had an experiment called SALJEX a long time ago. I forget when, but Argentina was very much involved. And it's because you have the mountains to the west and the plains, and then you've got a lot of moisture that you cap the unstable atmosphere. And because you're able to cap it, say, more than other places, the atmosphere gets exceedingly unstable. And so unstable that when the instability is released, due to enough heating during the day to let the clouds develop and get taller, you get massive storms, not only vertically, but also long lines of storms we call squall lines. And these lines of storms, which we've observed previously from low Earth orbit, but not with these instruments from geostationary orbit, can produce lightning rates of 1,000 flashes per minute for hours and hours and hours. And we know that you'll sometimes get windstorm damage, sometimes even tornadoes, hail definitely. And so they are spectacular thunderstorms, and you have all the ingredients, both geographically and environmentally, to get those kinds of storms here. And this will be our first chance with you to be able to observe the life cycle of these storms. And so we will learn a lot about, so how can storms become so intense? More intense than anywhere else. What's the secret sauce, as they say? What's magical about this area? So there's a lot of interest. So special research radars are being brought in. We have a ground-based lightning mapping system that has a number of stations that gives us the lightning channels in 3 dimensions. That tells us how much of the total lightning is going on, not just lightning striking the ground, which provides another validation data set for the satellite. So while you're running Relampago, you'll be asking us to collect special rapid scan imagery of the storms there, which will be much faster repeat or refresh rate than you might normally get, and there'll be more insight into how the storm's evolving by observing it changing so quickly. As an example, like storms will develop from just rain clouds into producing hail. That can happen within 2 to 2.5 minutes. So if your normal satellite scan is 15 minutes, you've got like 3 observations and a thunderstorm's gone through its whole life cycle. It's grown, it's matured, and then it's died. And so it's important to get these more rapid information. And then there'll be special research radars and other instrumentation in the field to help us understand the environment those storms are growing in, the attributes and characteristics of the storms themselves. And so it should be a unique and valuable data set that we can collect.